All right, so I'm Nathan. I'm at the American Museum for Natural History with joint appointments at the Simon Center for Computational Astrophysics and Stony Brook University, and I'm going to continue to talk about binary stars and galactic nuclei with a focus on dynamical hardening, so single binary interactions. So the first thing I think we can all agree on is that binaries are pretty effectively destroyed on relatively short timescales in galactic nuclei. And to first order, you might expect that really only roughly contact binaries should survive for any appreciable amount of time. But we can ask, so if you truncate your orbital separation distribution at the hard-soft boundary, how long should all of these effectively contact binaries survive for in the galactic center? And so we show some results here for the local group galactic nuclei. The different colors are showing different collision scenarios, so main sequence collisions in red. The single binary interactions are shown in blue. And we're showing distance from the cluster center on the x-axis. And the basic idea is that if you integrate over these curves, you get the total number of binaries destroyed within 2 parsecs from the galactic center every million years. And so for the Milky Way galactic center, we find an average rate of about 1 binary destroyed per million year. And so this is assuming all binaries are almost in a contact state, so at the hard-soft boundary or below. We assume a binary fraction of 1%. And so what this amounts to is that your binary shouldn't really be hanging around for very long. The exact calculation's sensitive to what you put in, your orbital period distribution, things like this. But to first order, I would expect if you form any population of binaries, you'll probably destroy all of them, even the contact ones, just dynamically within less than a gigayear or so. And so this is because if you throw a single star at something like a contact binary, you're going to get a collision. There's pretty much no way to avoid that. And this is ignoring Kozai and all these other different mechanisms that can also serve to stimulate mergers and ultimately deplete your binary fraction. So the general consensus, I think, is that binaries are efficiently destroyed in galactic nuclei. And I'll come back to this point as I go on. But this is talking about stellar main sequence binaries. What happens if we consider stellar mass black hole binaries?
Could you just clarify? So gigayear, this is the short time that you're talking about? So you're saying things are destroyed really short, and then you said it's about a gigayear time. So
well, so I showed.
It's relatively short depending who you're talking about,
Right.
right?
So I was just looking at your plot and actually seeing that we agreed quite well. It's just yeah. So.
I just wanted to clarify.
Sure. Yep. So for an old population, for example, you might not really expect a lot of binaries to be around. Maybe you. I mean, this is ignoring binary formation though, which could be something interesting to consider. Okay, so we're going to address the question. So black hole binaries, because they're more massive, the orbital separation corresponding to the hard-soft boundary can be but a factor of 100 times larger or so than for a main sequence binary. So we asked the question, in a galactic nucleus, how many 3-body scattering events does it take to harden a stellar mass black hole binary to the point of rapid in-spiral due to gravitational wave emission? So that is to get the binary down to the point where the time for in-spiral due to gravitational wave emission is shorter than the time for another direct interaction to occur. And as a corollary, we want to know how does the degree of anisotropy, or how much rotation you have in a nucleus, affect this rate and the number of 3-body scatterings. And so to address this question, consider the following toy model. So what we do, we consider a Milky Way-like nuclear star cluster, so same supermassive black hole, central density of order 10 to the 6 solar masses per cubic parsec, same velocity dispersion of order 100 kilometers per second. We put our black hole binaries at the influence radius, so of order a parsec away from the central SMBH. We assume component masses of 10 and 15 solar masses. We randomly sample the initial orbital separation between 1 and 10 AU, draw from thermal eccentricity distributions. And what we do is we run a series, 10 to the 4 Monte Carlo simulations with this initial setup. And for each one, we ask how many 3-body scattering interactions does it take to harden the black hole binary to this critical point where it's going to merge before another interaction takes place. And when we do this in the Monte Carlo simulations, we consider hardening due to both dynamical interactions as well as inter-encounter gravitational wave emission. And so this rather busy plot shows the results of that experiment. So this is all 10 to the 4 Monte Carlo simulations, assuming different angular momentum distributions for the scattering, so different distributions we draw from for the incoming single star. These are shown, the two extremes being the isotropic case, shown in red, and the planar case, shown in blue, as well as a few intermediate cases in between. So on the x-axis, we have the logarithm of the initial separation of each of our black hole binaries. And on the y-axis, we have the logarithm of the number of interactions it takes to harden it to this critical point. The solid lines show analytic estimates we calculated for this critical number of interactions, ignoring gravitational wave emission. So this is how many interactions it takes to wind the black hole binary down purely due to scattering. And we run the simulations, and once we get the results, so the shaded regions show all of our Monte Carlo simulations, and the red and blue dots show the binned means of these Monte Carlo simulations. Yeah. Right here. So that is formally where, for the velocity dispersion in the galactic center, this is the hard soft boundary at which your energy becomes greater than 0. Yeah.
Another quick question. Are your scattering experiments only with small enough impact parameters to give you a resonance state, or is it flybys also?
These are direct encounters. We do consider flybys perturbations, which effectively just increase the eccentricity without doing much to the semi major axis. And it changes the results a little bit. It shifts basically these points down a little bit because gravitational wave emission is a little more effective. You're driving up the eccentricity, so you get more circularization in between encounters. But this is no perturbations. This is only direct resonant interactions. So a few things to note. So gravitational wave emission does play a role, but the scattering, at least in the planar case, does a pretty good job. So the offset here, this is partially between, so that my analytic estimate shown by the solid blue line compared to the blue circles here. The blue circles fall just slightly below. This is partially due to gravitational wave emission, but it's also partly due to the fact that I assumed a peak escaper velocity instead of a mean. So the agreement is a little bit better. But the main thing that we found when comparing the difference that you get for scattering in the isotropic versus the planar case is that planar scattering is much more effective at hardening binaries. And there are two reasons for this. So in the planar case, the distribution of escaper velocities is broader. So the mean corresponds to higher ejection velocities. So on a per encounter basis, planar scattering is more effective at hardening binaries than is isotropic scattering. For this same reason, actually, the first interaction will harden a binary more in the planar case than it will in the isotropic case. And so in the planar case, on the second interaction, you have a smaller probability of disruption. So you have a smaller probability of drawing a velocity from your Maxwellian distribution that gives you a total energy greater than 0. And so that's largely what's causing a lot of this disagreement. So if you go beyond the hard soft boundary here, a lot of these binaries are just being destroyed. So we find when we run the isotropic case, we found that most of our binaries were actually disrupted long before getting to merge, whereas a significant fraction more of the planar case actually made it all the way into merger. Right. Sure. Yep.
I would expect that to be, so if you do hardening, you have sort of a constant hardening expression of your binding energy. And the cross-section of your binary shrinks with the hardening of your binary. So the probability or the time between interactions become larger. Why is this then a straight line, basically, the red plus? I would expect to see the probability distribution of your encounter rates back in that distribution.
So you would expect to see.
The fact that if your binary shrinks, that the time scale between encounters becomes larger. So this is the number of encounters.
Right, but gravitational wave emission becomes more efficient, so that's what's pushing it down here. These guys don't need very many interactions since they start with a small semi-major axis, and so gravitational wave emission is more efficient in driving them to merge. So we have a cutoff here, a lower semi-major axis, where once it's below that, we don't care anymore because we know that the interaction time will exceed the time for in-spiral due to gravitational wave emission. So basically, so technically, binaries haven't actually merged by this point, but by our analytic calculations, they will before the next interaction. Maybe we can talk about, I guess, exactly the shape that you would expect from this, but you've got a few competing effects that are affecting the distribution. Gravitational wave emission at the short end, disruption preferentially up here by drawing velocities that exceed the hard-soft boundary, and then the effects of actually hardening due to the scattering. Maybe we'll come back to it. Yeah, so one thing you have to worry about is if the ergodic assumption is upheld in all of this, and I think that's where the conversation should probably go. But
Is that an integrated result, or was it dependent? Where on the orbit around the supermassive black hole these binaries are?
at the influence radius.
Okay, sorry.
So, right. So, okay. So the point so far is just that it's relatively easy to destroy binaries, right? So it doesn't really matter how you're looking for them. If you're looking for binaries photometrically, spectroscopically, or indirectly from gravitational wave emission, if you're seeing large amounts of binaries, I think this immediately begs the question, where are all these binaries coming from? What's their creation mechanism? And so that was just something that I think I wanted to emphasize here. We talk a lot about destroying binaries, but it might be interesting to talk a lot as well about creating binaries, since, well, in globular clusters, you see binary fractions of less than 1% often in the core photometrically, and there are ways that you could try to get around that by exchanging in remnants that you wouldn't be able to identify them photometrically as binaries anymore. But in general, since given how interesting binaries might be in this dynamical environment, ways to generate binaries could be a good thing. It might be needed, in fact, to explore to explain observations if we're seeing a lot of them. Okay, so how can you make binaries in sort of the exotic ways that you might not think about if you think about a purely spherical stellar system coming from globular clusters, as I often do? And so one way you can do this, as Doug touched upon, is in AGN disks. And so the basic, very hand-wavy argument here is that you can get very similar to what happens in the planetary case. You can get migration traps in AGN disks. And because of this, inward disk migration, type 1 migration, can cause black holes and other objects to end up stuck in the migration traps where they can accrete, they can grow in mass. Other objects can come in and meet them in the migration trap. Gas dissipation can then facilitate the binding of the two objects, and you can create binaries in migration traps, potentially. Although some collaborators, Mordecai, Mark, Maclow, Barry, McKernan, Savick 4, they're getting into the nitty-gritty details of trying to simulate this in detail. So this hasn't actually been simulated, but in principle, it seems worth thinking about more. In particular, because there's the potential to set up a nice scenario where you have planar, preferentially planar scattering. And so your binary, you would expect to have its orbital semi-major axis more or less aligned with the disk. Stars come in through the disk. So you have this planar scattering with very low relative velocities at infinity. And because of this, you're unlikely to dissociate the binary. And so this is a scenario where dynamical hardening actually becomes efficient in a potentially very high velocity dispersion environment. The key point that you need is to grind down all of the stellar orbits into the disk on relatively short time scale, certainly less than the disk lifetime, but less than any interesting time scales for the black hole binary. The reason being that if you're inclined at a 90-degree angle to the disk, you're coming in with a local Keplerian speed and you'll just ablate the binary. So you need everything in a disk, basically. Okay, so one other question I'd like to address, just to plug some recent work by a graduate student of Rosalba Perna working at Stony Brook University, Yihan Wang. So Yihan asked the question, you have a central supermassive black hole. you have a binary around it. In this case, it's 2 stars, but it could just as easily be a binary black hole. So this setup from before. And now we add an additional massive perturber orbiting outside this trio. And we ask, what could the role of the perturber be in terms of affecting relative rates of mergers of the binary, or hypervelocity stars, or tidal disruption events? And so Yihan ran a series of these M-body simulations. He was focused on mergers and HVS. So in this plot, he's actually focused on just the mergers. And so one of the things he was finding, so for example, if you're in an AGN disk, this is a scenario that might come up. You can grow black holes at different migration traps within the disk. And the outer massive object can actually affect the inner binary in various interesting ways. So if we look down at the inset shown here, so the lightly colored regions are showing the regions where most simulations resulted in a merger, and the dark regions are showing where the initial configurations of the setup where no mergers occurred. And these 2 bottom plots are showing the inclination angles. So I out, this is if you just take the binary as a single star and you want to know the inclination of the outer orbit relative to the inner orbit of the binary about the central SMBH. And this is the inclination of the binary's orbit around the primary SMBH. The basic idea being, if the binary center of mass is inclined in the outer orbit in just the right way, Kozai is activated, and it can push the distance or the pericenter of the binary inward, which can in turn activate Kozai from the inner object, and this can then drive mergers to occur if the setup is initially right. But we don't seem to see this at much larger mass ratios due to breakup of the binary. This is eccentricity of the binary's center of mass. It's this orbit, the purple orbit. Yes.
That includes GR for everything?
Post-Newtonian.
Yeah. First one for each orbit?
Yes. And kind of the cool thing one of the cool things that Yihan found, and so this is a plot showing as a function of mass ratio between the inner SMBH and the outer SMBH, the ratio of different hypervelocity scenarios. So you can make a single hypervelocity star. You can eject 2 unbound single hypervelocity stars, or you can even eject a hypervelocity binary. And so Yihan's finding that as he goes to large mass ratios, the binary gets ejected whole without merging, quite a large fraction of the time. But as he goes down into these low mass ratios, the relative fractions start to disappear. And so this is now where we're actually focused, since if you care about the galactic center and this type of scenario happening in the galactic center, I think the parameter space is such that there could be an IMBH orbiting the central SMBH, but the mass ratio has been constrained to be somewhere down in here, 10 to the minus 3 to 10 to the minus 4. And so our simulation, so it turns out that in this regime, Yihan only found of order 50 hypervelocity stars in total, which means the statistics were not quite good. Out of those 50, we found 0 hypervelocity binaries. So now the question will be to go back and redo the simulations until it starts to become non-zero down here and try to figure out relative fractions of hypervelocity binaries relative to hypervelocity single stars. But the basic idea being, if your S stars or anything else is a contact binary or a relatively close binary, and there's the possibility that it gets ejected before merging or anything else, can get ejected whole.
So they don't have how were these integrations done?
These were done with the point-extended Ruth Forest-like integrator, and Yihan compared a whole bunch of integrators, but yeah.
So did you try also this R chain?
AR chain? No, that's the one we haven't tried, but that's what we're going to do next, because that's probably where you want to go, right? Yeah.
I really recommend it.
Yeah, I know. Anyway, that's the project for next week, actually. Well, we have a workshop next week where we're going to do this. So, yeah. And I think the point here was just that. So this is showing hypervelocity single stars, so all the hypervelocity events, and then this is just the hypervelocity binaries, with the point being that when we're in the active Lidov-Kozai domain, binaries can drift inwards and merge more often. And so in the binary case, you want to basically just keep them out of the active Lidov-Kozai domain, because then you merge the binaries before they're ejected as a binary. And that's it.